So then we can start. Okay, we are happy to have Arkadij Bojko from ETH in Zurich, and he will speak about wall crossing for Calabi-Yau fourfolds and probably some applications. So please.
Yes, thank you. So as the title suggests, I've been working on proving wall crossing for sheaf-counting theories and Calabi-Yau fourfolds, and more generally for all kinds of triangulated Calabi-Yau four categories, and some computations and applications of it. The structure of the talk is going to talk about the construction of the virtual fundamental classes at first, in the setting of Calabi-Yau fourfolds. Then I will move on to describing some modification, some different way of working with vertex algebras than what Joyce did. So I'm working rather with families of vertex algebras. And then,
well, if you think that we know what Joyce did, so you are certainly overestimate us. Yeah.
But you had Alexei Latintsev in this seminar.
Yeah, we have so many seminars. So in general, for example, we know so in very general terms what Joyce did, but I forgot all the details. Especially, I think I at the time I thought that it's not quite the right framework. But so if you recall somehow.
Yeah, so I will not recall his. I will just give. It's not such a big difference. My whole point is that I'm adding a family version. So Dominic constructed vertex algebra. I'm constructing families of vertex algebras, and I'm wall crossing using them. But it's essentially the same idea. So I'm not.
Okay. All right.
Making up too many things. So you will see what he did anyway in it. And then. Yes, once I formulate the vertex algebra, I will give a description of the wall crossing formulae in terms of them. First, I will explain on an example what you can do to actually get explicit formulae and compute almost everything you would want. And then give a more general statement in a setting of Calabi-Yau categories, assuming that some assumptions hold. And yeah, everything is obviously working with some stability conditions, and I will describe the ones that I like to work with and the ones that I will prove it for. Finally, I will give a brief idea of the proof, and the main difficulty being in this point 4.2, which stopped Dominic actually originally from writing it into his big 300 pages long paper. So yeah, I will not talk about this part too much. I will just sprinkle it along the other sections, the further applications. So let me begin with the local models for the moduli spaces of Calabi-Yau fourfolds, which lead to the virtual fundamental classes. So start with your Calabi-Yau fourfold, meaning that you have a trivialized canonical bundle.
Is it compact?
Not necessarily. So I will be working with something which is quasi-projective, and I will be looking at compactly supported sheaves more generally, or compactly supported complexes. But you can, for simplicity, assume that it's compact. If you want.
Actually, for simplicity, I would assume that it's non-compact, because compact are more complicated.
Well, no, actually, the computations using the vertex algebras become simpler in the compact case.
Okay, well, it's
so. But I will explain how this works later. So yeah, and then choose your moduli space of stable perfect complexes. Preferably, you either have some sort of an action on it so that the fixed point locus is proper, or that M itself is proper. And then the work of Pussybraff, Joyce, and with some contribution from Autonomous described the local model of this moduli space as being locally cut out inside of the X1, so locally around each perfect complex E. It looks as if it were embedded inside of X1 of E with E, and then there is an isotropic section into the X2 group where the fact that it's isotropic comes from the observation that X2 has Serre duality on it. And the Serre duality obviously induced this pairing B from X2 squared C. And it is then the result of the statement of Pussybraff Joyce, or also reformulated in Autonomous, that this section is indeed isotropic.
Stable with respect to what stability?
Anything. Just any reasonable thing. I will talk about the particular setting that I'm working with. Dominic has these very general weak stabilities. I'm not a big fan of the weak stability he uses. I prefer some sort of Bridgeland stability conditions. And that's the ones.
So some sort of Bridgeland stability, or maybe whatever, Bayer, Toda, whatever.
Yeah, so I'm using exactly Bayer's polynomial stability condition in this work. And once you have this section, then the vanishing set of it is precisely our moduli space. Now, this introduces a notion of orientations that you wouldn't expect in the complex setting. That's because you have this isomorphism from the determinant line bundle, the determinant of X2. Well, rather, if you square this pairing, if you take determinant of B, you get determinant of X2 squared being isomorphic to C. And now you can take square roots of it, and you have a Z2 choice of these square roots. And this gives you your orientation torsor at each point E in the moduli space. Now you can glue these choices, these Z2 torsors together to get a Z2 bundle, an orientation bundle on the moduli space. And you can ask whether it is trivializable, which is equivalent to saying that the moduli space is orientable. Now the point is that in all the cases that we care about, it is true that these are orientable, that the moduli spaces are orientable, and this was showed by me in the compactly supported setting for quasi-projective Calabi-Yau fourfolds, and that was generalizing the work of Joyce, who proved it in the projective case. So once you have these orientations, then originally Borisov-Joyce, using some derived differential geometry together with derived algebraic geometry, cook up virtual fundamental classes. Then Autonomous rephrased it in a much more algebraic geometric setting. And these classes sit in their virtual dimension 2 minus chi EE. So you can see that it's not 2 minus 2 chi EE, it's actually 1/2 of what you would expect. And this is because of this whole point that you have an isotropic section. You're kind of taking half of your X2 group.
Yeah, I remember that when we defined this cohomological whole algebra with Maxim, so in 4-dimensional case, you should fix a square root of X2, kind of polarization for this Nekrasov story. And then, yeah, everything goes well abstractly, even for higher stacks. Okay, good. Thank you. Yeah.
Yeah, so the setting that it is proved is exactly for the higher stack of
Yeah.
perfect
But it's
complexes,
kind
which
of
are compactly
intuitively,
separated.
it's kind of clear. So then just the details are questionable. Okay.
Yeah, I mean, actually, it's not. I wouldn't say it's that clear. I mean, you need to go to gauge theory and then pull back, use some
No.
multiplication
I mean,
operation.
it's just by analogy. If you think by analogy with a three-dimensional case, and
yeah, but in the three-dimensional case, you don't even need to do properly.
no, you need
you
need an orientation data in 3D case,
yes.
which is you should prove it somehow separately. In
But isn't this just the
four-dimensional
paper of
case,
Nekrasov Okonkov?
no, in four-dimensional cases, if I remember, you do not have a perfect abstraction theory. I mean, because of X2, but you can polarize X2, probably that's what you say. This is UB.
Yeah, that's this
And
isotropic.
take one half of it. Yeah, I think it's pretty clear, but I don't know, maybe I'm missing something. Yeah.
So in the three-dimensional case in the Calabi-Yau threefold, it's basically the idea of Nekrasov Okonkov proving
No, in 3D
the
case, it was
orientation
an
data.
idea of Maxim and myself. In five-dimensional case, it was Nekrasov and Akunkov, which they did geometrically, and we did it with Maxim very abstractly, in the framework even more general that you are talking about. Now, in four-dimensional case, Nekrasov, I remember he asked me, how to define this integral of the moduli space of instantons. And in 4D, it wasn't clear how to define even this moduli space, but for that you need to polarize X2, kind of, because by third duality, kind of, X2 is the only part which does not have an inverse dual to it. But then if you split your symplectic manifold into halves, then it is. No, I mean, I think it's clear. It's kind of real polarization. It's pretty clear.
Yeah, I mean, the fact that the orientation bundle exists is clear, but the fact that it's trivializable is actually a very difficult proof.
This is, yes. I was talking only about existence, of course, not trivial. Okay, yeah, thank you.
Yeah, because you need the fact that it is trivializable to construct.
Yes. Otherwise, the moduli space is not well defined because you might not have a section, and so you have to work with higher whatever stacks. It's more complicated. Yeah. Thank you. Yeah.
Okay. Yes. So here I now globalize the point of view that I described in the previous slide by having a vector bundle over a smooth moduli space, or not moduli space, but a smooth ambient space, and having an isotropic section of a vector bundle where I'm using that my vector bundle is SONC. This already implicitly assumes orientations because, as this footnote says, if you start with an ONC bundle and have orientations, you get SONC bundles.
Yeah, even for the vector spaces.
Yeah. And the section is still isotropic, and now you can actually cut out, you might hope that your moduli space is globally cut out as a zero locus of this section. So if you want to, in this simple case, this is a very trivial, this is a very simple example of what the moduli space could be. And if you want to construct a virtual fundamental class, or if you want to describe it, then you can take an isotropic subbundle, a maximal isotropic subbundle of E with respect to B. Or equivalently, you could, if it doesn't exist, this lambda, you could take the musical isomorphism from E into E star and compose with an anti-linear map from E star into E induced by a Hermitian metric, then you get a map which is an anti-linear real structure from E into E, and the associated real subbundle consists of the fixed elements with respect to sigma. So now once you have either one of these descriptions, the push forward of the virtual fundamental class of M back into the ambient space A is just the Euler class of lambda, if it exists. And if it doesn't, it's the Euler class of this real subbundle. And the real subbundle has orientation induced by a choice of isotropic subspace if they exist, because there is an isomorphism between them. So you have something real isomorphic to a complex one, you have canonical orientation. So this is just the toy model, toy example of what the virtual fundamental class in this setting looks like. And of course, you can now define them for any moduli space, as long as you have orientations and we prove that they exist. So now, to actually do some wall crossing, I will need to work with vertex algebras and more generally, as I promised, with families of vertex algebras. And these consist of the usual vacuum vector and the linear operator, which is the translation operator on the vertex algebra. But now, because I'm working over a formal disk, I have family of state to field correspondences, which are maps from the vertex algebra into its endomorphisms, or rather into its Laurent series, valued in endomorphism, but this time it has the additional variable use, this additional U dependence.
So it's flat family, yeah?
Can you tell me what the V sub dot here is? Are you talking about the, some kind of gradation of V?
Sorry, I didn't quite understand the question.
What the V sub dots here is that a
yeah, so this is a graded vector space.
Okay.
So my dot will denote some sort of grading always.
Okay.
And yeah, so these are a family of state field correspondences, and these incline to be degree 0 maps, which additionally are continuous with respect to the U-adic topology, such that if you extend it, yeah, I mean, obviously you can extend it to a full map from the power series with values in V bullet. But one of the important axioms of the vertex algebra, of the families of vertex algebra, is that if you act with state field correspondence evaluated on V, then it is a linear map from V bullet into the power series in U valued in the Laurent series, and not the other way around. So this is important to actually make sense out of things like out of the later axioms.
So in some sense, if you go to the generic fiber over a formal disk, it's the same as consider the vertex algebra of a two-dimensional local field.
Yeah, exactly.
Yeah, okay.
And this is just a family of it. I mean, but I don't think it needs to be flat. I mean, you can have all sorts of derivatives in U. There is no such restriction.
Oh, okay.
So this can be thought as a sheaf on the formal disk, not puncture, right?
Yeah, it's a sheaf on the
formal disk
on the puncture disk times the formal disk, and a section of it. It's a section. So these Y's, usually a vertex algebra.
The U actually is the uniformal disk, not puncture.
Yes, I understand, but a vertex algebra on its own, this YU can be described as a section of a vector bundle on a puncture disk. You know, because you have this meromorphicity here, right? But you add the extra parameter, so you have a puncture disk times the unpunctured disk.
Yeah, Arkadij, may I ask you kind of side question? So
Sure.
vertex algebras, it's sort of a very outdated language. So nowadays it's better to speak about chiral algebra so they can be globalized, and instead of this disks in Z, you can consider a global curve. So if you look for a family, do you need still it to be formal over U, or you can consider another global curve over U and to build really some two-dimensional object?
I mean, I could build a two-dimensional object. It just did not feel necessary for the applications that I was going to use it for. And I was aiming mostly for proving something and then applying it.
Mm. All right, all right. Mm-hmm.
Right. So these VUNs that I introduced here, these are linear maps from V bullet into V bullet U for all n. And these are now required to satisfy the usual axioms. So you have the vacuum axiom, meaning that the vacuum is the minimal energy state. And also if you act with a state field correspondence on a vacuum, then you recover V plus something which has higher powers of Z. And then you have also the translation and covariance. So this nothing changes here again. And the only difference really in the usual axioms that you would define is that the locality statement, because you can't simply define, I mean, you can't formulate the usual locality statement if you just include the variable U. Instead, what you need to do is you define these truncated fields. So you look at fields which only see a few powers of U for any up to any k, and then it makes sense to define locality. So now you say that the commutators of these two state field correspondences, if you take large enough power of Z1 minus Z2 and multiply it by it, then you get 0.
So this, just to understand, this T in the power n in the square brackets, it means what? It's a coefficient of this.
Yeah, so my y depends on T here, right? So it's T is formal variable and I can expand it, and I'm taking the nth coefficient of this power series in T.
Okay, thank you.
Yeah, so as I mentioned already, it's very important to have this truncation to even formulate the locality statement, but also it's very important to have the right order of these coefficients, because if you took this, you wouldn't be able, for example, to accommodate the applications that I need to. And this will become apparent later. So how do we construct this? This is really very much an idea of Dominic, and my contribution is this additional dependence on you. So I will just go over it, over essentially his construction. So you start with your underlying vector space of the vertex algebra being this. You start with the moduli stack of all perfect complexes on X, and you take its homology and you shift it by the virtual dimension of Mx for each connected component. So then the three ingredients that I described, the vacuum vector is just the inclusion of the 0 element inside of Mx once you push forward in homology. And the translation operator is obtained from this scaling action. So you have an action of point mod gm on Mx, which rescales the automorphisms of each object inside of your stack. And since you know that the homology of point mod GM, this is just your power series in T, in some variable T, then you can define the translation operator by pushing forward T box times V. So if you just start with a homology class in MX and you take a tensor product with the generator of homology on point mod GM, push it forward, then that gives you the translation operator.
So this time the T has a degree 2, that's the homological degree, right?
Yes, correct.
Thank you.
But the shift is relative anyway, so it doesn't see the fact. It means still degree 2 also on this shifted homology.
Yeah, this is somehow corresponding to the earlier, the degree of the Z was negative 2. It's
yes.
due
Yeah, so that this cancel out. Yes.
Thank you.
So the more complicated construction now is this family of state field correspondences. And these are obtained from first taking the direct sum map on the MX cross MX, because you're working with a triangulated category. You obviously can take direct sums of objects and induce corresponding map on stacks. But you also need a K-theory class theta, which sees, in some way, it sees the obstruction theory. So it looks at each point E and F in MX cross MX. It's given by X bullet EF. It's given by the X complex of between E and F. And really what it does is, if you pretended that the summation sigma is an embedding, then it sees the virtual normal bundle of it. Here it should be saying sigma, not phi. And this theta is clearly additive. If you take direct sums of objects here or here, you get direct sums of thetas. And it's also multiplicative with respect to rho, which rescales the automorphisms of E and automorphisms of F. So that's an important property, actually, to be able to construct vertex algebra. And these would be essentially, yes?
But the X, which is not equivariant in the E direction, that's when you take the X tab.
Yes.
And it's contravariant with E. So try to
yeah. So you get weight -1 here for the point mod GM action, and here you get weight +1 for the point mod GM action. But this is what I mean by multiplicative. I didn't want to go into that detail too much.
Okay.
Right. So if you took this is the data that Dominic needs to construct vertex algebra. Now I add something else. I add an equivariant K-theory class omega U. Again on the product MX cross MX for the trivial action, and EU being the weight 1 line bundle. And now these must satisfy the same additivity and scaling property that theta did, this with respect to the point mod GM action and the sum. And if you take the sum of theta and omega U, then that's what I denote theta U. Now, just the next point is simply for notational purposes. If you take if you take the connected component of the stack M associated to alpha, which is a semi-topological K-theory class, then you can define a pairing on the semi-topological K-theory, which I denote by kappa, by mapping kappa, by defining kappa alpha beta to be equal to the rank of the restriction of this equivariant K-theory class to M alpha cross M beta. And then just, again, to simplify notation further, I write chi omega to be the sum of chi and kappa. So this final bullet point is describing how the orientations interact with taking direct sums, which is important for the construction of vertex algebras. And again, this is already an idea of Dominic. So if you fix choices of orientations, which you know that exist for each connected component M alpha of this orientation bundle on it, O alpha, then because you have additivity of X2 groups, once you take determinants, these middle terms, this X2, E2, F1, and X E2, F2,
XE1.
there is some mistake here. Yeah, so this should be saying
FE1.
Yes. Right. So these will cancel out by Serre duality once you pull back to the diagonal. So if you pull it back to the diagonal, you can use Serre duality here to cancel these two terms out. And this tells you that there is an isomorphism from the product of the orientation bundles on each component alpha and beta into the pullback along the sum, the direct sum morphism of the orientation bundle. So using these data that I just described, I define the families of vertex algebras on V-bullet by this formula. So you can see here some signs in front. Then you have these signs epsilon, alpha, beta. These are the signs comparing the two trivializations, the two choices of orientations. One is the one obtaining by pulling back, and the other one is obtained by taking products of orientations here. So these are Z2 choices so that you can compare them by a sign. And then you can push forward along the direct sum morphism, and your translation operator now twists the first contribution inside of the homology of mx cross mx. But before you do that, you cap with the total trunk class with variable z minus 1 of this equivariant K-theory class theta u that I had here. So here, this A that I added is kind of for later purposes because I restricted to hearts of triangulated categories, which I denote by A. This is the formula defining the family, and you see you have here the U dependence, and here you have the two Z dependencies. And you can check that these indeed satisfy the axioms that I just wrote down. So this data defines a U family of vertex algebra. And here's an explanation of why I needed the axioms to be formulated the way that I have. So consider the example.
Interrupt you on the previous page. So what the U dot here is that the homology of the modulus.
Yeah, V bullet is just the homology. Yes, correct.
Of the entire the stack.
Of
right?
stack, yeah. It can be the higher stack of perfect complexes or just the stack of coherent sheaves. As long as you have some sort of additivity on it, then you're fine.
Thank you.
Now, what's just a general
consider
question?
now this example.
What's the role of this twisting by the line bundle? Why do you need it with respect to?
So I'm twisting it not by line bundle, by this equivariant K-theory class.
Yes, but this U, it should come from certain line bundle. I think you wrote it
so
in
this
your
is
previous.
So this was just, I'm not twisting by it. I'm just saying that this U is the first trunk class of the trivial equivariant line bundle on MX cross MX.
Yeah, but if I categorify, I will certainly need the line bundle itself. So what's the role of it? Kind of, because this is something
I haven't thought
new.
about it. It's just for me, it's just a trivial, it's just a nice way to state it. I have not gone into that direction.
Okay.
But I can explain why I'm choosing the axioms for the families of vertex algebras the way that I am. And this is because if you take this naive sort of omega u, where you just take e to the power u, just the line bundle, times some additive number of copies of the structure sheaf. So remember, we needed some additivity under direct sums. That's why I put this chi alpha beta here. Then you can see that the total Chern class is just 1 plus z minus 1 u to the power chi alpha beta. And clearly, if chi alpha beta is negative, you will have infinitely many powers of z minus 1 appearing. And you want to avoid that in any sort of definition of vertex algebras. So that's why I say that I'm looking at power series in U, which are valued in Laurent series in Z. And this is the simplest example for why why this is the order that I'm phrasing things.
Mm-hmm. So they take the Laurent series first, and the Laurent series are the coefficients of the U, right?
Exactly, exactly. This is why there is
not
no
the other way
contradiction.
around. Mm-hmm.
Exactly, that wouldn't work. So yes, as I said, this is why it was needed to state this theorem, which was extending Dominic's ideas. I would like to just point out that our proofs are rather different of this fact. I'm using precisely the axioms that I wrote down to prove it. He's writing it down in coefficients and using Borchards' definition.
Yeah, may I ask you a question? I recall I asked Alyosha himself, and actually I asked, I think, Dominique long ago when he explained all that stuff. So it looks like one important structure is missing, at least it's not used in the definition. You have this class theta, something like x, something like something corresponding to the bundle on the product of the on the Cartesian square of the moduli stack of objects and applications, but you do not have the potential, which actually you have for any Calabi-Yau category. It's not number valued for.
No. So I think we had this conversation over email. So you don't have any sort of potential over Calabi-Yau 4 categories. You have them over Calabi-Yau 3 categories.
No. I do have potential for Calabi-Yau n category. It's not really. I mean, at least it's not a function, you know, because you can define Chern-Simons for any odd dimensional Calabi-Yau. So you just write this generalized Chern-Simons action for at least for any odd dimensional. This is true. Probably for 4-dimensional you don't have it, but there is a problem. Maybe it's rather maybe it's a question to the discussion part. So maybe just go on. Because there will be some question. Yeah, okay.
Good. So now, obviously, the vertex algebras are good, but to Walcross, you actually need Lie algebras, at least the way that Dominic originally phrased it.
So then I'm confused here again. So for Walcrossing, you certainly do not need Lie algebras. So Dominique's original idea, it's kind of, it was, I mean, no, you need.
I mean, you get the whole algebra, but then you restrict to some subalgebra of it, which is actually a Lie subalgebra.
But you don't need it at all for Walcrossing, so absolutely not. You
I
need,
mean,
it's
in this
enough
framework,
to have. It's enough to have whole algebra itself.
Here you don't have whole algebras. I mean, Alyosha has this work where he intertwines them, but I don't. Here, the Lie algebras are the more natural way to start with the.
Maybe, but I just objected the fact that you really need Lie algebras for Walcrossing.
I mean, you can take always the enveloping algebra, then you get rid of the Lie algebra.
No, but the whole algebra, it's not, in general, it's not an enveloping algebra of any Lie algebra. So, but anyway, okay, you construct some Lie algebra. Okay, good.
So I actually construct a family of Lie algebras, because this usual construction that Borchardt gave of vertex algebras, if you apply it to families of vertex algebras, these formal families, then you actually get families of Lie algebras. And this is done by taking the quotient with respect to the action of the translation operator, and then taking, if you recall, the state field correspondence had these VUNs, which were operators, linear operators in the vertex algebra, and you define the V bracket to be acting on the class inside of the quotient of V and of W by lifting them and applying this operator VU0 to W and taking its class. And the dependence U transitions. And you can actually just go and look at any old proof of this fact and see that it works actually in families of formal disks.
So actually, this is a great. It's kind of a DG algebra, right?
It's a what?
It's a kind of a differential graded algebra, but with a differential.
Well, my U is degree 0, so I mean it is a graded, but it's not a differential graded.
Whether the Jacobian additive depends on which degrees of the this are.
Yes,
No, but
there is
it's
no
graded,
differential.
but it's a trivial differential.
Yeah, I guess, but that's a bit overcomplicated. Thanks. Right. So, in fact, this has a geometric interpretation, and that is that outside of the 0 component, this Lie algebra is the result of taking the rigidification of the stack mx with respect to this point mod gm action, and then taking its virtual, it's then taking its homology and shifting it by the virtual dimension. And here the virtual dimension is a bit tricky, because if you quotient down by the point mod gm action, you should only get a difference in the virtual dimension compared to the usual mx stack by 1. But this differs by 2. And this is because I'm taking not the natural obstruction theory on the stack m-rich x. I'm taking something which is again symmetric. It's basically it removes 2 copies of the gm. One which is a result of the removing by the point mod gm action, and the other one because you need to remove it to recover something symmetric. That's what this VDMC stands for. Now, of course, if you, as I already mentioned before, if you just set this k-theory class equal to 0, you recover just the usual non-family version of vertex Lie algebra constructor of Dominic. And then with that, I would like to move on to an example of how you could apply this to actually make some statements about virtual fundamental classes. Almost out of very little data, you can compute a lot of things. And for that, you start with, I mean, I chose the example that I worked out, and that is the quad schemes. So if you look at if you take a rigid stable vector bundle E and consider the 0-dimensional quotients of it, well, here I even take a torsion-free sheaf instead of vector bundle. Then this moduli space has a universal pair, and using this universal pair, you can embed it into the stack mx simply by requiring that the pullback of the universal perfect complex here is this universal pair. And then push forward the homology class, the virtual fundamental class of the quad scheme, to give you a homology class inside of the stack, inside of the vertex algebra and then push it further into the quotient. And the point now is that the usual definition that Dominic gave, that would give you this wall crossing formula in terms of the Lie bracket. So you have some sort of partition of the number of points, some coefficient, and then you have Lie brackets between the vector bundle E and fundamental classes, which are counting zero-dimensional sheaves of n1 points here, and here nk points, and it's an iterated bracket. So this is the usual thing that you would see. It's just now phrased in terms of the Lie algebras out of vertex algebras. Mm-hmm. But of course, you would like to compute something on the right-hand side, because you don't know what either of the sides is. So what you do is you twist the vertex algebra by this equivariant complex EU x, well, something that looks at each point of mx cross mx as x between E and F twisted by L, plus some almost trivial correction terms, which I will not discuss much further. And the point is that if you take E to be equal to the structure sheaf, you just recover from the quad scheme the usual Hilbert schemes of points. And now you can pull back this K-theory class along the diagonal and restrict it to the Hilbert scheme by its inclusion into MX. And this gives you a rank n vector bundle, which is just EU times ln. So ln being this tautological vector bundle, which is obtained by having the universal zero-dimensional sheaf twisted by the pullback of L to x times Hilbert x and pushing forward to the Hilbert scheme. This gives you rank n vector bundle, which is now, it comes with this equivariant parameter. And if you work with this setting,
you get the L, which one is the tautological bundle? The L and
yeah, this is the ln is the tautological bundle, which is defined by this formula on the right hand side.
Okay.
This is the universal zero-dimensional sheaf.
The L, I mean L.
No. So ln is the tautological vector bundle. L is some choice of a line bundle.
You first make a choice of a non-bundle, and the F.
Yeah, so here L is some sort of a line bundle. This should be stated somewhere. So L is some sort of a line bundle on X.
So not the dualizing.
No.
Non-equal bundle or anything.
No. So if you twist by this equivariant K-theory class, then the wall crossing formulae change. You get
so
something.
What do you change when you say wall crossing? You should move from the space of stability structure.
Well,
so
no. So I'm not changing the stability. I'm changing actually the vertex algebra and the Lie algebra and the objects that I'm wall crossing with.
So I do not understand what do you call wall crossing then, sorry.
Well,
you
I am crossing wall from zero-dimensional sheaves.
Okay.
So I'm into Hilbert schemes of points. But now they're not just degree 0 virtual fundamental classes. So they see much more than just one invariant. There are all kinds of invariants that you can integrate. And therefore you can wall cross with all kinds of invariants. Sure. You have the same you have the same stability condition, but if you change your vertex algebra, it changes the invariant that you wall cross with. And here I was wall crossing with just the plain virtual fundamental classes. That's the idea.
Arkadij, probably there is a terminological problem, at least for me, because I've been doing this wall crossing business for quite a while, and I didn't have this terminological problem with other people, including physicists. So let's kind of Specify, what do you call wall crossing formulas? Because you don't need any vertex algebras for that. Wall crossing formulas, and I think it was in the even in the Dominic, this original intuitive
Yeah. So
picture.
I don't
you,
mean his
you just change.
original.
Okay, but then what is wall crossing according to you?
Yeah, so that's what I say. So you have some homology classes inside of the stack NX.
Okay, stack of
And you
all
have the
objects.
yeah. Or rather on its quotient by this translation operator. That's where you have some classes, some homology
Okay.
classes. And now as you change stability conditions, classes on which are corresponding to semi-stable objects on one side are related by the Lie bracket on this quotient.
Yeah, but hold on. But
Classes
you
on the
just said
left-hand
that
side.
you do change stability conditions.
Yeah, I do. But here I have just one family of stability conditions.
All right, but this is what wall crossing formula
Exactly.
is about. You move, you cross
Yes.
the wall, and so you
Exactly.
recalculate. And so your left-hand side doesn't depend on the stability condition. Right-hand side does depend because of this SS semi-stable. And so then you recalculate, and that's wall crossing for. Okay, so then we do not have this terminological conflict. Yeah, all right.
Yeah, so my point wasn't that I'm somehow wall crossing from this formula to this formula. These are two different formulae which use the same family of stability conditions to relate different invariants because I'm changing what the vertex algebra and therefore the associated Lie algebra is, because I twisted by this EULN. And the twist, so the new invariants that you get to wall cross with after twisting are written down here. So this is just some power of u capped with cu minus 1 with the total trunk class with variable u minus 1 of ln.
Yeah, I'm still
right
struggling to understand it. Even if we accept this Joyce outdated picture with Lie algebras, you have just one, whatever, Lie algebra, but a whole algebras where this wall crossing story happens. Now, when you introduce this parameter u, it affects what? It does not affect the stability data.
No.
It just does affect your vertex algebras, but in Lie algebras as well.
Yes, I mean the Lie algebras are constructed out of vertex
which means that if I prefer to think in terms of the whole algebra, which is a more fundamental object, you have a family of whole algebras instead of just one. Is it correct?
I'm not sure these Lie algebras are directly related to whole algebras. There is no, I don't believe there is work on that precisely.
Yeah, your understanding, and that's also my understanding, that U is parameterizing the, just to see how the family of the vertex side.
Yes, the U just parameterizes.
Yeah, but you see, for wall crossing in general, you do not need any vertex algebra structure. It's a byproduct of something. Yes, and you can use it, but it's not a fundamental.
There is a good reason for working with vertex algebras, and this is this work on Virasoro constraints that I have with Miguel Morera and.
So what's the reason for work? What's the reason to work to look for vertex algebra?
You know that vertex algebras have conformal elements.
Yes.
And conformal elements define primary states inside of the vertex algebra.
Okay.
And primary states, if a virtual fundamental class is a homology class, is a primary state, then it's equivalent to saying that it satisfies Virasoro constraints.
No, it's not a big deal, because in more general story, your fundamental class is always a vacuum vector for some vertex algebra, which may be more complicated than just lattice vertex algebras, which Dominic considered. So it's always the case that it's a vertex, some vacuum vector. That's okay, but it's still not the wall crossing formulas. It's a different
no,
kind
but the
of
whole point is
statement.
that you can use the fact that you have wall crossing formula and the compatibility of the Virasoro constraint with respect to the B bracket to prove that if you start on the right hand side with Virasoro constraints, you get Virasoro
there is
constraints on the left hand side.
something not good in this picture, because
yeah, let me ask clarification.
Okay. Yeah.
So the V in this change and or the twisting, that the V dot does not change because the homology classes,
Yes,
but
that's just homology of the
algebra
set,
structure
correct.
changes, right?
Yes, correct. That's because I'm
and
adding
also
this
the
EULN.
I see. So the change seems to be only in the U direction, but does not change the Z in the vertex.
No, so it changes completely the vertex because
that's correct.
If you recall, I can go back. I add this whole omega U to it. So this was the old vertex algebra,
and
now I'm adding this full omega U. So it changes it completely, the vertex. Oh, it changes it quite a bit, and then it adds this additional U dependence.
And you also mentioned about the Virasoro element. So this also changes the Virasoro structure and the central charge.
Yeah, so
as well.
Actually, I did not think about
I see.
What this does to Virasoro conformal element, but I think what it would do is you still would have a lattice vertex algebra. And just, I mean, no, I actually know you still have a lattice vertex algebra, and I do expect that you just get a different conformal element and different Virasoro constraints, which are now again compatible with wall crossing. So this is actually a good question, something I should look at more. Right. So my point was to explain that if you now start with this twisted vertex algebra, instead of relating just virtual fundamental classes, you're relating now these kept products with respect to these total Chern classes of tautological vector bundles for a line bundle L. Now, if you just take the 0th coefficient of U, then you get the formula, which is just on the left-hand side, this integral of the top Chern class of Ln with respect to the virtual fundamental class. And on the right-hand side, you just get a Lie bracket which only depends on the L that you started, because you took out this dependence on U. So you start from something which is a number, no longer a homology class. This is just a number. And you can actually compute out of it what these fundamental classes are. So if you go back to the previous slide and use Dominic's formula, then you can actually, starting from some very simple invariants for line bundles, compute the 0-dimensional sheaves, or the invariants counting 0-dimensional sheaves, and out of it compute every topological data you would like about the quad scheme for any vector bundle E, any rigid stable vector bundle E, its virtual fundamental class. So are there any questions about this up till now?
This particular thing is nice. I mean, it's a nice idea. You got kind of the general framework, but probably it's better to postpone it until discussion Q&A part. Yeah.
Now, I want to actually, this was just an example, really, because I wanted to explain the idea on how it works before I actually formulate what I'm proving. And what I'm trying to prove, or actually what I have a proof of, but I just basically need to write it up, complete writing it up, is if you start with a heart of a triangulated category, a Calabi-Yau 4 triangulated category, which can be enriched to a Calabi-Yau 4DG category. And if you have some connected set of stability conditions, countably many codimension 1 walls, then assuming that some long list of assumptions hold, you will have wall crossing. And these assumptions, the two main ones that I would like to focus just for the purpose of the talk here, is that first one is that you need to have some family of exact subcategories indexed by k, together with functors whose domain is ak, mapping into this into, well, basically the complexes of two vector spaces. This is D0, 1. These are complexes of representations over A1 in degree 0, 1. And therefore, I'm saying just vector spaces in degree 0 and 1. Such that if you start with an object E bullet inside of AK, and you look at its automorphisms inside of T, then this can be expressed under the functor HK as morphisms inside of the dB of A1. There is a canonical such as a morphism. An additional requirement for this to work is that the rank of HK bullet has to be always greater than 0. And the second assumption is the one that is actually difficult to prove. So this one is rather simple to construct. But the second one, which is difficult to actually check in many cases, is that you require that for each stability condition in this family, in this open set of stability conditions, there is a stack of semi-stable objects for each class alpha, which is proper in the sense that it satisfies the evaluative criterion of properness and admits an open embedding into the higher stack of the triangulated category T. So this properness part is something, evaluative criterion of properness is something that can a priori be non-trivial, well, rather difficult to prove. So you need theta stratifications to do that in general. And right. So now with these assumptions, the point is if they hold, then you have some sort of classes inside of your Lie algebra, inside of this quotient of the homology. Here it should be saying Q because that's how I defined denoted the quotient previously. And these classes, they count the semi-stable object of class alpha, and they can be defined as long as the entire stack lies inside of the stack associated with the category AK for some fixed K out of the assumptions that I gave previously. If you have no strictly semi-stables, these classes need to satisfy this condition that they are given by the virtual fundamental class capped with the top Chern class of the restriction of this equivariant K-theory class that I was working with previously. Oops. Right. And these virtual fundamental classes, these are just push forwards of usual virtual fundamental classes for the moduli spaces of stable objects into the rigidification of MX. And you could define these invariants, but now they need to satisfy some wall crossing formulae. And this is the actual point, that once you define them, then for any two stability condition in W0, in this set of stability conditions that you work with, you can express the semi-stable virtual fundamental class for sigma 1 in terms of classes for sigma 0, as you vary from sigma 0 to sigma 1 in a family. Now, I'm using this notation, this Langle, the left bracket and right bracket, like the brackets, because I'm not really working with just virtual fundamental classes. I'm working with these invariants, which are the result of twisting by the top term class. And what are these stability conditions that I'm working with? I don't know how much time I have, because now I'm realizing that this part is rather long.
I don't know if you can briefly explain, because I believe that people should know what's Bridgeland stability conditions, maybe even some know what the polynomial stability conditions. So if you kind of can explain without too many details what is your modification, it will be sufficient, I believe.
Yes, okay. So the polynomial stability condition is just something which you have some central charge on your triangulated category or on its heart, which is a map from your K group into the polynomials valued in the upper half plane. And a particular construction of such a central charge, which Bayer called standard polynomial stability condition, was given in terms of some perversity function. Once you have perversity, you can define the perverse sheaves by this condition, or by this condition that you look at.
Coherent perverse sheaves, not constructive.
Yes, correct. Yes, coherent perverse sheaves, which are the perfect complexes satisfying that their ith cohomology is supported in some dimension specified by this perverse function and has no torsion outside of a p minus 1i, where the perversity function is a map from 0 to 4. 4 appears here because I'm working with Calabi-Yau fourfolds to z. So the example is the usual one that you use for DTPT wall crossing, which is the perversity function 0, 1, 2, 3, 4, and this gives you the torsion pair that gives you the category.
Is there in general semi-orthogonal decomposition associated with the perverse function?
No, I don't think so. I mean, this is just some generalization of what a tilted, what a torsion pair is.
Yeah, but what you have written, it's exactly semi-orthogonal decomposition, if I understand correctly. In this particular, this is why I asked you whether in general it's also the case.
Yeah, so I don't. I thought the semi-orthogonal decomposition. So this means that the maps from here to here are zero.
You do not have homes. I mean, in one direction, something.
Yeah. So I do believe that yes, you actually do. You do get a generalization of the same picture here. So you do get morphisms being zero into one direction. That's because of this torsion condition that I described.
That's what the torsion pair is about.
Yes,
but generalization is a semi-orthogonal decomposition of triangulated category, and so that's probably what's going on.
Kind of. So in the standard case, of the standard construction that Bayer gave of these polynomial stability conditions, they just needed some sort of phases inside of the complex plane, such that once you take multiply them by a power of -1 to the power of the perversity function, then you always lie in the upper half plane, and as you increase the dimension of the support, you move in the clockwise direction. And I work with a slightly more appropriate setting for working with Calabi-Yau fourfolds, which is I introduce this stair function, and then I twist. I start with some naive perversity function, and I pre-compose with this stair function to give a new perversity function. In terms of it, I define again this heart and this bounded T structure, as was on the previous slide, but this time I don't look just on phases of or just on complex number. This time I actually have morphisms from degrees of cohomologies determined by the stair function. So it's a preimage of some number, and I sum over all the degrees which lie in the preimage inside of the cohomology, and I have a group homomorphism from this into complex numbers. And then the new central charge is expressed in terms of this set of more group homomorphisms. Now again, to make things well behaved, you need some sort of nice behavior when you rotate in the clockwise direction, and that's precisely the statement that the action of rho kk as you act on complexes with as you act on sheaves with fixed dimension of support, as you increase it, it moves in the clockwise direction. And this slide I can just say quickly. So there is this theory which lifts this construction of Pandare-Thomas of the PT stable pairs on Calabi-Yau threefolds to Calabi-Yau fourfolds, which was done by Bay, Kuhl, and Park. And you can define them again in terms of some co-kernel and torsion condition for the target F. And my point is here on this slide to just give you an example that the stability condition that this more general framework of stability condition compared to what Bayer called the standard one, this gives you something which accommodates wall crossing between their PT0 pairs and the PT1 pairs. And this is described by this central charge that I described in the definition. But I will just quickly just give a picture of it. So what it does is it spreads the less than or equal to one-dimensional contribution across the upper half plane, and then the structure sheaf, the phase of the structure sheaf, changes from, well, because you need to take the negative sign, it changes from the phase being plus 1/2 to minus 1/2. And yeah, here you have PT1 stable pairs, and here you have PT0 stable pairs. So you can actually get wall crossing formulae, you can prove wall crossing formulae for these invariants. So yeah, that was the stability condition. Can I just quickly go over the proof, or am I already running out of time?
Well, it depends how quickly you can do that.
So how much time do I have?
No. It's not I mean, you can go over the time. It's not a problem. It's question how, if it's just a technical thing, or it will kind of will give us some new understanding.
Well, it will explain to you what this how to define this virtual fundamental. So gave you some. I told you that there are some homology classes that satisfy some Walker-Thing formula, but I didn't tell you what these classes are.
Oh, okay, all right.
And this tells you what they are, and so it describes how they are defined.
Yeah, go ahead. Yeah.
So, and just to define them, the whole point is that you need to work only with Joyce-Song pairs, which correspond to this quiver mapping from a vector space into your sheaf. This QMS, it's just a master space quiver that you need to introduce to prove that these classes are in fact independent of choices. Because you end up wall-crossing inside of the master space after localization, and that's how you get the vertex algebras. So actually, this is also very important, because this this quiver QMS is exactly what leads to the vertex algebras. You can read off the construction of the vertex algebra, its definition, from some localization for the moduli space of semi-stable object for this quiver. So here you put 3 vector bundles, or rather 3 vector spaces. You have morphism between them. And here you put your perfect complex. So one perfect complex for both dots, but you get then morphism from the vector space. And if you recall, I had this definition on the previous slides of this, in this assumption, I had these functors HK. So what you do, you look at morphisms from the vector space into HK applied to your perfect complex here. And this gives you then a moduli stack of such objects, which I denote N. And you can in some sense pull back the polynomial stability conditions that I described previously.
Arkadij, I somehow lost, because so far it was geometry. All right, now you started to talk about quivers, and then I'm lost.
Yeah, so I'm looking at these objects, which are the triples of vector spaces.
Okay.
The perfect complex.
Perfect complex on what? On my fourfold or what?
Yes, on your fourfold.
Okay.
And then you apply to this perfect complex these functors HK that I described. Yeah. These give you perfect complexes of vector spaces.
Yes.
So you can consider morphisms between each of these bullet points. And now between each of these vertices. And now what you get is a moduli stack of the triples, which consist of the perfect complex of the vector spaces and the morphism between them. That's a moduli stack.
Mm-hmm. Okay.
And this is, you can pull back the stability condition, you can get semi-stable quiver pairs.
No, but I am confused about stability condition, because now you're basically just in the category of complexes of vector spaces.
No. Yeah. I have, this is a category of triples where you have the sheaf or the perfect complex, then vector spaces, and then morphism between the vector spaces. So you don't forget the sheaf. You still have it here as an element.
Okay. So then you have some stability on sheaves.
You have stability here, and now you can extend it to give you a stability on all of these, on the full triples.
How do you extend it?
It's some generalization of Joyce-Song stability.
I have no idea what is Joyce-Song stability condition. Never read the paper.
Have you heard Bradloff's stability condition?
No. In geometry, I understand, but you are talking about.
If you look at Mochizuki or Bradloff pairs.
Yeah.
Then that stability condition, it's generalization of their stability.
Yeah, all right, but so you use quivers just to depict
vector space, like copies of
all
OX
right,
minus K.
all right.
Yeah, you should think of OX minus K, copies of OX minus K being here.
Yeah, it's not something about quivers, it's just a way to depict stability on sheaves on, say, surfaces or whatever, fourfolds. Yeah, okay, good.
Yeah. Yeah, correct. And now the point, I mean, this is a technical point. You need to prove that you have obstruction theories on these moduli spaces that give you virtual fundamental classes. And this is the statement of the theorem. And moreover, they need to satisfy this compatibility diagram, which will tell you that there is some virtual pullback, which was proved by Park, obtained by, so if you start with something which only contains stable objects, then the virtual pullback gives you the virtual fundamental class of the stable quiver pairs. And the obstruction theory here is exactly this F composed mapping to F naive and then mapping to L, the cotangent complex of the stack of quiver pairs. So once you have this, you have virtual fundamental classes which satisfy a nice property with respect to pullback and push forward. And you can define now for this QJS quiver, you can define by starting with the invariants, counting this quiver pairs, capping with the relative tangent bundle, with the top trunk class of the relative tangent bundle, and pushing forward the resulting homology class to the Lie algebra on the stack of perfect complexes. And using these classes, these are homology classes, you can actually now define all these invariants that I was wall crossing with. Now, obviously, if you have no strictly semi-stables, these invariants, these are just related by some constant expressed in terms of this functor hk that I previously mentioned, multiplying the usual virtual fundamental classes. So you start the induction from this formula. You know what the virtual fundamental class is, and you know how it is related to this omega k alpha. And then you proceed by some induction on the measure which counts how unstable, like how strictly semi-stable your class can become. And this is then you define, using this induction, the classes, the fundamental class, the virtual fundamental classes alpha for alpha class alpha and stability sigma in terms of this omega sigma alpha minus some sort of expression in terms of the Lie bracket. And here you see that these are summons alpha I, and all of them are strictly less strictly semi-stable. So this is why the induction works. So in the end, you get all the virtual fundamental classes, all these invariants counting semi-stable sheaf on the left-hand side defined in such a way. And in here, I purposely avoided specifying U and H to simplify the formula, but every class here depends on a choice of H and is also depending on U. And this H, to get rid of this dependence of H, is why you need this this master space quiver, which I had on the previous slides. And it is also where this vertex algebra and Lie algebra appears. So this is kind of the main part of the proof of the wall crossing. So if you start with the master space quiver, and you use the two different functors, H4 and H5, to define these morphisms from OX from the vector spaces into some vector spaces associated to the perfect complexes, then using the action on this edge of the quiver, so on this morphism, you get 3 fixed point loci of the stack of quiver pairs. One is setting this arrow equal to 0, and that's related to the invariance omega alpha sigma for the functor h4, which I had here on the top. And then one which is setting these morphism equal to 0, and these are just these invariance omega alpha sigma, which are defined in terms of the functor h5. And then you have some additional set of fixed points, which in which case you split the perfect complex, which was the perfect complex at these black nodes, you split it into summands, one on each node. And these summands then lead to this Lie bracket of the resulting invariants for the functor h4 and h5. And now, if you do this computation with this localization computation, you get this formula that the difference between omega sigma alpha for the functor h4 and omega sigma alpha for the functor h5 is just the Lie bracket coming from the third type of fixed point loci, which comes from splitting alpha into its direct summands. And if you plug this into this defining formula of the invariants m sigma alpha, which was defining them by induction, then you can actually prove that the result is independent of the choice of h. So that's where the vertex algebra is appearing, or rather the Lie algebra that comes from the vertex algebra, and that's how you define these invariants. So that's all for me.
Okay, thank you very much. So, are there any questions or comments? Actually, I have, I don't know whether it's a question or comment, probably both. You see your, I mean, you work with 4-dimensional Calabi-Yaus, like, and you said that non-compact are okay. So like take C4, 4-dimensional vector space, which is already interesting because it's related to this Nekrasov story. Now, if you do the dimensional reduction from 4 to 3, which does make sense in Nekrasov story, then there should be a specialization of your 4-dimensional picture to 3 dimensions.
Yes.
Now, in 3 dimensions, you do have the potential. Where it comes from?
Well, that I cannot answer you, actually. I know that you can actually, there is hope of proving DTPT correspondences, which are unproven using 4-dimensional so using 4-dimensional geometries and using this dimensional reduction that you're bringing up. But I don't see where the potential would come from. Actually, there is possibility because you can look at your C3 inside of C4 as a divisor.
Yeah.
Now, pretend it's your anti-canonical divisor in it.
On C3, it's difficult to imagine.
Yeah, but you think of P3 inside of P4.
P3 inside of P4 is okay. C3 inside of C4 is not quite okay. And for me, that's the main difficulty. I want in the Nekrasov story to have some P4 in the P4, but I don't know how to edit. Yeah, but anyway, suppose that I have some divisor, like let's imagine that the C3 carries some anti-canonical. Just imagine impossible, then what?
Yes. Then you have this description that if you forget the fact that you started with a Calabi-Yau and in fact pretend that you have a Fano fourfold, then the local model of this moduli spaces, so this thing that I described here, remember I had x1.
Oh, I see. It will be indeed.
It will be twisted by a potential.
Yeah, exactly.
And this potential will be pulled back from the potential on the canonical divisor. And that's where the interplay happens.
Okay, so yeah, it's an interesting point, which means that probably one should look in Nekrasov's story for some compactification to P4. And actually,
yeah, so this is something that I was thinking a little bit about. And
yeah, I thought about three-dimensional story, and actually this is my second remark, which is tied up with this one. You see, in 3 dimensions, when we work with a local Calabi-Yau, local 3-dimensional Calabi-Yaus, then we have some picture which resembles to what you explained, but and I'm wondering what's the relation between the two. So what's the picture in 3 dimensions? We have a chamber structure, for example, in the derived category of coherent sheaves, including this perverse chamber which you mentioned. And with each chamber, I can associate a vertex algebra. For different chambers, they are different, and the wall crossing correspond, of course, to the crossing of the wall between different chambers. But the fact that these vertex operator algebra structures on different chambers are compatible, it is based on the fact that there is a big cohomological whole algebra, which does not depend on this division of chambers. In each vertex operator algebra for each chamber, it is obtained from this cohomological whole algebra by certain constructions specific to the chamber. And so then indeed, if you want to count something inside of the chamber, it looks like you can use your vertex algebra. That's fine. But in fact, what's going on that you have a big cohomological whole algebra, and all the computations can be made inside of it. So this is why I kind of asked too many questions to that part of your talk, because for you, this vertex algebras, they kind of the essence for wall crossing which you do. But for me, it's a secondary object. So that's.
But so we had this discussion about the conformal element. I still don't understand how you would see any sort of conformal element from a whole algebra.
No. You said that your conformal element is not a conformal. I mean, you look for something like virtual fundamental class. And so you do not need really, if I understood you correctly, you do not need really to have a conformal element. You want to say something about this fundamental class.
Yes, but the formulation is that if you start with a conformal element, you take the associated Virasoro algebra of operators LK.
It does not have to be Virasoro. That's actually another objection to this Joyce formalism. Because when you do the reduction to 3 dimensions, you see the whole line of W algebras for which Virasoro is just one of them. And Probably
No,
you
but,
see.
This Virasoro algebra spanned by the conformal element is just a small subalgebra of the big lattice vertex algebra that you construct.
Okay. You
But
need
this is why it's interesting. So you pick the canonical, you pick a very natural choice of a conformal element inside of the lattice vertex algebra. That gives you a Virasoro subalgebra, and with respect to it, you get this Lie subalgebra of primary or physical states inside of your inside of the Borchert's Lie algebra associated to the vertex algebra. And
yeah, I see.
And these are every single virtual fundamental class that we have thus far looked at is a physical state with respect to it.
No, but the point is, I mean, again, I have rather three-dimensional intuition, so it may be should be probably modified. But in 3 dimensions, we have this AGT conjecture, generalized even AGT conjecture, and so which basically means that your virtual fundamental class, I'm kind of oversimplifying, but it's a vacuum vector for a representation of certain vertex algebra. And basically this is it. So you don't have to...
but this is because your virtual fundamental classes are in degree 0.
This I cannot tell you right away.
Because vacuum vector is in degree 0. But the whole point here is that virtual fundamental classes, in my case, they sit in they sit in various degrees.
Still, I'm not convinced. Well, at least let me say it kind of in modest way. There is a certain similarity between the story in 3 dimensions, which I just mentioned, and this is a generalized AGT conjecture. Basically, this means that you have a cohomology of certain moduli stack, or maybe even moduli space of semi-stable object on some category. On this cohomology, you have the action of, in general, cohomological whole algebra, but this can be upgraded to the action of a vertex algebra on this graded vector space. I cannot tell you right away in which degree sits the vacuum vector, and actually in general it can be many of them. But what this Nekrasov partition function and various generalizations, they indeed are such examples of such vacuum vectors.
When you say Nekrasov partition function, do you mean the one in 4 dimensions or?
Yeah, in 4 dimensions. Yeah, let's say in 4 dimensions, including this generalized instantons, which in fact comes from 4-dimensional Calabi-Yau. That story with this, he strangely call it Mamma, some strange terminology, but anyway, some generalization of cohomological whole algebra to dimension 4. So basically, I spoke to him like a few years ago about that stuff, and there should be some sort of generalization of AGT to this 4-dimensional Calabi-Yaus. And again, if you do have the chamber structure, then I would say that it should be similar to 3 dimensions. And so, I mean, at least some parts of your talk certainly resemble. Yeah. But since you learned by heart this Dominique's formalism, which I believe should be upgraded, okay, how to say it politically correct, should be upgraded maybe to some better formalism, then maybe you do not see this cohomological whole algebra perspective. You see,
I have no experience with whole algebras.
yeah, that's you should ask Alyosha. He does. Yeah, but the point is that you're right in the sense that you can think about cohomological or whatever any whole algebra as an sort of enveloping, maybe quantized enveloping algebra of some PPS Lie algebra. Actually, Ben Davison will give a talk next week on that topic here in the M seminar, and the convenient probably for UK time because he is in UK. And so then indeed there is some Lie algebra, which I'm not sure whether it's anyhow related to the Lie algebra of Dominic, maybe not. But having this BPS Lie algebra, you can do with it whatever you do with Borchards generalized Kac-Moody. In particular, you can try to build vertex algebras and ask the questions which you ask. So, I mean, you have a very nice picture, and actually I was really impressed how you was able to do whatever you've done with this Joyce formalism, but maybe you can look in that direction as well. Because our wall crossing formulas with Maxim, which fits in this whole algebra business, they really appear in physics in the way they should appear. Dominic's formulas originally were designed for computing some invariants, and that's how you applied it. But from our perspective with Maxim, these invariants, whatever dt, pt, or whatever invariants you have, they are secondary. You have some rather geometric object which you cut into pieces, and the way these pieces are glued together, you know, like cluster varieties, different tori are glued together. So the way they are glued, it is encoded in the collection of numbers. So which means that our wall crossing formula, they look completely different, and from what Dominique did. And the point is that if we try to rewrite it in the way of Joyce, we have too many terms which are actually equal to 0, which you don't need to count. Kind of, if you are a computer, you will certainly appreciate the saving of computer time when you work with our formulas. But it's a different approach. It's from this point of view, it's natural to think about these vertex algebras, as I explained, as chambers and blah, blah, blah. And also...
do you perhaps have a reference where I could start looking at it?
As for vertex algebras, you can look at our papers, 2 papers with Rabchak and
when you say our, you mean yours?
Yeah, mine with 3 other people. One is Rabchak, he is a physicist student of Gayota, and Yaping Yang and Gufang Zhao, 2 algebraists. And they have something about Nekrasov spiked instantons and about Calabi-Yau 3-folds, and kind of you can see what we mean, in which way these cohomological whole algebras are relevant to the story. And there was also this very old means probably 12 years old paper by Schiffman and Vassero.
Yes.
I forgot, I remember that it was 95 pages, but I forgot the title. It's where they proved this AGT conjecture for the first time. it's something probably also moduli spaces of instantons. I don't remember, but it's in the archive, so I can send you a precise reference. And this is how they proved this AGT conjectural Gayota-Tachikawa conjecture that something is a vacuum vector for the action of W algebra. This is prototype of what I mean. Even more classically, there was in the 90s probably the first in the area result of Nakajima.
So how is being of is it? So you brought up something being a vacuum vector.
Yeah, originally
constraints.
Originally, it's kind of it's a Nekrasov partition. It's a generated sum over some integrals over the moduli of instantons. All right, then you want to interpret it as a highest vector for some maybe generalized Kac-Moody. Or for some vertex algebra representation. The conjecture which comes from physics says what the answer is. It should be some W algebra of GLN and or beta R rank of the instanton, and for R equal 1, I think is just a Nakajima's result about the action of Heisenberg. It's a lattice vertex algebra, the one which comes from cohomology of Hilbert schemes. For R bigger than 1, the geometric action was not constructed, I believe, before Schiffman and Vassero, and slightly different, completely actually differently, Maulik and Nekrasov and the Kunkov. They are this book, actually, it's a book. Quantum groups and something else, I forgot. Okay, but then Nekrasov generalize the notion of instantons, and actually why I like your proposal, because original Nekrasov partition function, you take C cube, three-dimensional Calabi-Yau, and you take a divisor, C square in it. And so this is conventional, original Nekrasov instanton back to 90s, I guess. Now, if you have, for example, in C cube, 2 coordinate planes, or even 3, so you have something singular, which is not covered by Nekrasov story, but still there is an upgrade of that. In a sense, it's upgrade of Schiffman and Vassero, if you like. Or, for example, if you have inside of C cube fat divisor, C square with some multiplicity. All right, this is what we did with Diaconescu and two other people. Yeah, but then it's natural to look at C4. Nekrasov crossed instantons, it's not about C cube in C4, it's rather about C squared in C4, yeah, 6 of them.
3 copies of.
Yeah, but Nekrasov spiked instantons, it's about C cube. And so that's very interesting. So what we did with Rabchak and two other guys, we understood this dimensional reduction to C cube with 3 coordinate planes. But the most general case, it's open. And I'm really curious how to upgrade your technique to handle it. So it would be really interesting. Okay, sorry. So it now it's not a discussion; it's a private discussion. More questions? It looks like Zhongzhu has left, so then there are no more people asking questions during your talk. All right, last 10 seconds to ask a question. All right, then thank you very much. Very interesting talk.
Thank you.
Really. Okay, thank you. And this